So now we're going to look at some different properties of limits that will help us in solving a lot of the more complicated limits. So we'll just go ahead and start listing them here. So number one, if C is any constant, meaning that it's just a number, then the limit as x approaches a of C is equal to C, right? So, for example, if we have the limit as x approaches 1 of 5, it's just going to be 5, right? So it doesn't really matter what x is approaching in this case. It's just going to be whatever that constant is. And hopefully that would be pretty obvious from the, the graph of the constant function. So let's go ahead and do the next one here. And for this whole next batch, let's just go ahead and say, let the limit as x approaches a of f of x be L, and the limit as x approaches a of g of x be M. Okay. Just so we don't have to keep writing it all over and over again. Okay, so then the second law here, the limit as x approaches a of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Okay, which you could write as equal to L plus M then. So in other words, you can add the functions together first and then take the limit, or you can take the limit of the functions separately and then add them together. Okay. And we're going to actually be able to do this for pretty much every operation. Okay. So number 3 will be doing the same thing, but with subtraction. Okay, so the limit of as x approaches a of f of x minus g of x is equal to the limit as x approaches a of f of x minus the limit as x approaches a of g of x. Okay. Okay, and then we can also do this for multiplication. So the limit as x approaches a of f of x times g of x is the limit as x approaches a of f of x times the limit as x approaches a of g of x. Okay. So all of these laws will make solving complicated limits a lot easier, right? Because we can just break up the functions however we want to, basically, and take the limits of all the pieces individually. So again, if we are letting C be a constant here, this one's kind of a corollary to the last one, which is that the limit of as x approaches a of C times f of x would be C times the limit as x approaches a of f of x. Okay. So in other words, we can pull a constant out of there. I guess we didn't really need to define the L and the M here, but you could write like that this is equal to CL, this is equal to L, M, etc. I don't think we really need that extra part on it though to make sense of these. So now division, same thing. The limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x if m does not equal 0. M, again, being the limit as x approaches a of g of x. So it works over division. You just have to be careful about dividing by 0, like always. And then a couple more here. The limit as x approaches a of f of x to the n is equal to the limit as x approaches a of f of x, all raised to the n. So the first one you're raising f to the n, and then you're taking the limit of it. And this one you're taking the limit of it, and then you're raising it to the nth power. Okay. And this also works for roots. So I guess I don't necessarily need to write it again, because as we know, roots can also be a fractional exponent, right? So I think this is a good list of the common limit properties, and it can just basically be summarized as you can break them up over any of the operations that you want to, right? Addition, subtraction, multiplication, division, and exponents. So let's just take a look at how we might use some of these laws. So some of the easier cases first. So let's say we have the limit as x approaches -3 of 4x plus 2. Then we can take the limit as x approaches -3 of 4x plus the limit as x approaches -3 of 2. And this one right here, you can just do direct substitution. I mean, really, you can even break that up more into the limit as x approaches -3 of 4 times the limit as x approaches -3 of x. So you could just keep breaking these down as far as you want to. But we can see this one's -12. This one is just going to be 2. So this one will be -10. And now we can do another one here. So the limit as x approaches 2 of 2x squared minus 3x plus 1 over x cubed plus 4. So you could break this up as much as you want, basically. And, you know, in practice, you might not want to necessarily break this up. You might just want to do direct substitution. But when you're doing direct substitution, you kind of are implicitly using these laws. Like you're kind of saying that this is the limit as x approaches 2 of 2x squared minus the limit as x approaches 2 of 3x, etc. Right? So this is the limit as x approaches 2 of 2x squared minus the limit as x approaches 2 of 3x plus the limit. Obviously very tedious to write out the limit every time. This one we could say it's the limit as x approaches 2 of x and then cube it. Right, so we could use that power rule as well. Plus the limit as x approaches 2 of 4. So like in here, we're technically using the addition rule, the subtraction rule, the quotient rule, the power rule. We could break this one up with the multiplication rule. So we'd be using all of them essentially in here. We have the constant rule as well, right? So this one is equal to 8. This one is equal to 6 plus 1 over, it's going to be 2 to the 3rd power plus 4. So we get 2 plus 1 is 3 over 12. So we get 1/4. Okay. So again, it's functionally the same thing using these rules as direct substitution. So this is just kind of like implicitly what you're doing when you do direct substitution. You're technically using these limit laws to completely break these functions down. You could even add a rule in here. Some books like to say the limit as x approaches a, we'll call it rule 0, of x equals a. And then once you have this rule, you could break these down completely into all of them would essentially boil down to either the 0th rule or the first rule here, right? You either get it in terms of just to x eventually or just the constant term. So like this one, the limit as x approaches 2 of 2x squared could be the limit as x approaches 2 of 2 times the limit as x approaches 2 of x all squared, right? And then you're only really, you're breaking everything back down into that 0 within that first rule. Obviously, it's a little more tedious to do it that way, but it definitively shows that this is the actual limit.